Welcome to today's Explainer. We're diving straight into the incredible continuous loop of chemical and electrical energy. We're going to see exactly how batteries power our world, and conversely, how electricity can literally force chemicals to change their state. It's this absolutely fascinating balance of power, and we're going to break it all down.
So, here's our roadmap for the breakdown. We'll start with chemicals making electricity, then tackle the math of potentials, look at electricity forcing chemical reactions, break down the rules of conductance, and finally, we'll wrap up with real-world batteries and rust. Let's get right into it.
Section 1. Chemicals making electricity, or spontaneous power.
You know, the whole concept of electrochemistry really hinges on this fundamental duality. On one hand, we have spontaneous or galvanic cells. This is where chemical energy just naturally transforms into electrical energy. Think of the battery running your smartphone right now. On the other hand, we have non-spontaneous or electrolytic cells. That's where we actually have to pump external electrical energy in to force a chemical reaction to happen. So the core question is always, do the chemicals make the electricity, or does the electricity force the chemicals to react?
Let's look at the classic Daniell cell for a second. At the negative zinc anode, oxidation occurs. It's losing electrons. Over on the other side sits the positive copper cathode, where reduction takes place. The electrons travel spontaneously from the anode over to the cathode, and boom! That flow gives us an electrical current we can actually use to do work.
But here is a really fascinating problem. You set up this beautiful Daniell cell. The current is flowing perfectly. Your little light bulb is glowing, and then, well, it just suddenly stops working. Why? As the reaction progresses, a sort of pain develops in the system. Positive zinc ions build up excessively around the anode, while a relative negative charge accumulates around the cathode. This massive charge buildup creates internal resistance, a liquid-liquid junction potential, or LLJP, that completely halts the flow of electrons. The reaction literally chokes itself out.
Enter the salt bridge. This simple little piece of equipment is the ultimate painkiller for our cell. It's basically a porous tube filled with an inert electrolyte, like potassium chloride. It acts as a mediator. It's constantly dropping negative chloride ions to the anode side and positive potassium ions to the cathode side. This completely neutralizes that charge buildup, completes the internal circuit, and minimizes that restrictive junction potential. The salt bridge is exactly what keeps the power flowing smoothly.
All right, moving to Section 2, the math of potentials and calculating that power.
In a perfect laboratory setup, we measure standard potentials. But real life isn't standard, right? Concentrations change as a battery gets used. To track this, we start with the thermodynamic relationship between Gibbs free energy and cell potential. Then, we substitute in the standard free energy equation. And by dividing the whole thing by negative NF, we arrive at the Nernst equation. This formula is essentially a master key. It lets us calculate exactly what the voltage of a cell will be at any given concentration or temperature.
Section 3. Electricity forcing chemical reactions. Let's talk about the electrolytic cell. So, when we flip the script and connect an external battery to force a non-spontaneous reaction, say if we're purifying a metal, we need to know exactly how much substance we're actually moving. Faraday's laws give us the exact playbook here. The first law simply states that the mass deposited at the electrodes is directly proportional to the total electrical charge you pump in. That's just current multiplied by time. The second law takes it a step further. If you pass the exact same current for the same amount of time through completely different solutions, the weights deposited will perfectly match the ratio of their equivalent weights. It just makes electrochemistry so perfectly predictable. Section 4. The rules of conductance, which is all about moving ions. There is a really stark contrast between strong and weak electrolytes. Strong electrolytes, like standard table salt dissolved in water, are 100% dissociated right out of the gate. If you dilute the solution, their conductance only increases slightly, mostly because you're just giving those already free ions a little more room to maneuver. But weak electrolytes, like acetic acid, only partially break apart. Now, if you dilute them massively, approaching what we call infinite dilution, their conductance jumps sharply. Why? Because all that extra water actually forces more molecules to break apart into charge-carrying ions. But that sharp jump for weak electrolytes creates a massive mathematical challenge. We can't directly measure their maximum conductance because, well, you can't realistically dilute something infinitely. Kohlrausch's law solves this puzzle beautifully. It states that at infinite dilution, ions are so far apart they don't even interact with each other anymore. Each cation and anion makes a definite, independent contribution to the conductivity.
Because of this, we can literally piece together the maximum conductance of a weak electrolyte just by adding up the known values of its individual ions. It's a really elegant workaround.
Which brings us to Section 5, Batteries and Rust. Let's look at real-world electrochemistry.
First up, primary commercial cells. These are the spontaneous batteries you use once and then toss. The classic dry cell, using a zinc anode, yields about 1.5 volts and powers everyday things like your TV remote. But check out the mercury cell. Its voltage stays perfectly constant at 1.35 volts throughout its entire lifespan. The reason why is pretty brilliant. The overall chemical reaction doesn't involve any ions in the solution changing concentration over time. The variables in our Nernst equation don't shift, so the voltage never, ever drops.
Next, we've got secondary cells. Think of the heavy lead storage batteries used in cars, or those nickel-cadmium batteries in your power tools. These cells are totally reversible. When they're discharging, they act spontaneously, turning chemicals into power. But when they're empty, we plug them into the wall. By applying external electricity, we force the electrolytic process to kick in, driving the chemical reaction perfectly in reverse to restore the battery. However, this spontaneous power isn't always our friend. Rusting isn't just physical decay. It's actually an unwanted spontaneous electrochemical cell forming right on the surface of an iron bridge or your car door. The iron acts as the anode and oxidizes, sending electrons flowing right through the metal itself to a cathode spot. There, atmospheric oxygen reduces to form water. Those iron ions then oxidize even further into iron oxide. It's literally a tiny destructive battery eating its own container.
So how do we stop these unwanted power loops? The simplest method is a barrier coating, just painting or oiling the metal so oxygen and moisture can't even reach it. But the most ingenious method is electrical protection, specifically galvanization. Here, we coat the iron with zinc. Because zinc has a higher oxidation potential than iron, it steps up and acts as a sacrificial anode. The environment will ruthlessly attack and oxidize the zinc instead of the iron, sacrificing the coating to completely protect the structural metal underneath. It's basically electrochemical self-defense.
Let's end with a glimpse into the future of power. Look at this number, 70 to 80%. That is a massive figure, and it represents the incredible operational efficiency of hydrogen-oxygen fuel cells.
Unlike traditional combustion engines that lose tons of energy as heat and noise, fuel cells are incredibly elegant. They take the chemical energy of hydrogen and oxygen gases and convert them continuously directly into electricity. There are no moving parts, no burning. And honestly, the absolute best part? The only byproduct of this highly efficient reaction is pure, clean water. By fully mastering electrochemistry, we complete our ultimate, perfectly clean power loop.
We've mapped the entire journey today from the absolute basics of a Daniell cell and the math of potentials to the destructive power of rust, all the way to perfectly clean fuel cells. Which really leaves us wondering, if we possess the fundamental blueprint for highly efficient, clean energy that produces literally nothing but water, how soon will our entire world run completely on these perfect electrochemical loops? Thank you for exploring this explainer with me. Keep that curiosity sparked, and I'll catch you on the next one.